what is the built environment and why, where's like the data science for good in all this. So built environment, think of it as generally right now projects that can be built on this land. So that can be a road, or a power line, or a data center, and they have to all answer the questions, where can it go and what does it affect? And this is important because there's a whole environmental review process that happens that you may not see, right? But what happens, well, who authorized it, right? Like who even made this happen? And these reviews are actually quite large, multi-year, and multi-communal and public land management undertakings. There's a lot of agencies on the state and federal and tribal land levels that are all kind of jurisdictionally involved in this process. And although what's kind of interesting in the time period we're in right now is that agencies are under increasing pressure to complete high-quality reviews faster and cheaper. And the benefit, though, the good news is, though, there's a lot of geospatial information that is abundant, and AI is transforming geospatial infrastructure for government. So we're in a very exciting time, and so, what if we could use geospatial information and AI to streamline siting and permitting by making all this information ready for a world of foundation models, embeddings, and geospatial agents. So this is the goal. But first, how much do you know about your Washington history? Are there any, give me some projects that you think generally, like thematically, have been built in Washington. Any you can shout them. Any general thoughts? Dams, okay, what else? Bridges, okay. Any other? Highways? Overpass, okay, great. Okay, so you guys are nailing it. Just Columbia River Basin, just in the last talk, right? There's been a lot of projects built around there. Puget Sound and ecosystem restoration projects and environmental monitoring and hatcheries have been approved and built. Ferry routes, terminal traffic, your link, that's nice, right? Your avalanche structures. Fish passageways, Hanford out east, so a lot of variety and hundreds of projects have been built in Washington. But think about this now for the whole United States. So that's where we're going to go next. So how does this happen in Washington and how does this happen in the United States? Like what is involved in siting, reviewing, and permitting? And how much effort and labor and cost is going into it? So first there's like generally the siting process. There's siting and environmental screening, so where is the action, what's the area of influence? This involves actually quite a few authoritative data sources like government agencies. Think about your NOAA, your National Wetlands Inventory data, your floodplains. All of this data is essential to helping applicants be able to decide, okay, where can I even build to begin with, in addition to their own personal data or more restricted data like your SHPO records. But next comes the reviewing process, and the reviewing process is, what resources are going to be effective if you go build somewhere, who are the stakeholders, where are these stakeholders, and what are reasonable alternatives for what you're building so you can assess the impact. And what you can kind of start to notice is, so the green dots are $100K to $100 million projects we're looking at. This is how expensive it takes to do a review versus your yellow, which is $10K to $100K. So it's quite expensive, and it can take years to be able to go through the review process. And this is where the bottleneck really is. And a lot of agencies have been historically involved in this process. Agriculture, commerce, defense, energy, Washington State has a lot. But then if you make it through this and you survive as an applicant, you get to go to your permits. And your permits are, what federal, state, local permits you can gather that you can go out and start building, and under which regulatory authorities, and what are the timelines and requirements. This is where you get very law-like, very regulatory, your Clean Water Act, your National Historic Preservation Act, your Endangered Species Act, your state permits, all extremely important in this process. So it's quite long. So if you ever want to build something, this is what it looks like. And then it happens across the US. So yeah, the numbers and the costs and the time really add up. And you're looking right now at 6 decades of review projects on US lands. This is what at PNL we've been able to digitize and put for you all into a standardized view. And really, what does it look like on the other end for us? It's paperwork. It's literally documents, like hundreds and thousands of documents, millions of pages, and what I'll get into today is maps. Millions of maps have been created by geospatial contractors or analysts that have been part of this process to help support the environmental review process. So let's get into that. And real fast, what do we do then at PNL? We do a lot of products to help streamline this process. So first is we have our GeoAI pipeline. So you hear about how do we take this very unstructured data and actually literally just put it on the earth. None of this stuff is like actually GIS yet. How do we standardize all those document data so it becomes also metadata and attribute data for your geospatial data? And then also we're heavily using model context protocol tooling. I think there might have already been a talk, if not already. A talk on this, you should go to it. It's very new tech about how you can federate data sources in a way that's very readily available for agents and LLMs. And then on top of that, we build tons of applications, up to like 8 right now. But these are some of the main ones relevant to this talk. We have our search NEPA, our currency, and our write NEPA. These are kind of like your query retrieval tools to help quickly retrieve documents and geovisualize them. And then drafting, how do you help draft these documents that have been this long process. Okay, now we can start with the data and what it looks like. So this is what it looks like on the ground. You have your documents, you have thousands of these, and within these documents you have your text, you have your tables, and you have maps. And so you're in a very multimodal space. Yay, if you're a data scientist, this is so exciting. I love this, right? And we try to parse these documents and use LLMs or VLMs, and I'll get specifically to the VLM part, to be able to standardize and get something that's accessible for agents and models. But first, okay, how do you pick your model? This is very unique, maybe. In the field, it's not just text data, you're dealing with geospatial data. There's a lot of geospatial models to consider. First is your frontier multimodal vision language models. These are like your generalist multimodal models, but they're not like a scientist, you know? They're not like readily high impact for scientific discovery. And then you have your open multimodal models if you want to be able to fine-tune open weights. But then what's kind of interesting to me is you also have your geo-foundation models that are emerging. So you have these that are built for the physical world. They're meant to be, either Earth observation native, so they're specific to spatial, spectral, and temporal understanding. These are like your Preethis or your Earth 2s, and they're very fascinating to me. But the catch is that your data has to be pretty much already, on the Earth, geospatially referenced, and GIS objects. So we sadly can't use these. So we have to go with the middle ones. But what's the challenge then, right? So there's so much challenge in using VLMs on maps. The challenge is that maps are extremely abundant but heterogeneous. They can vary in types of either symbology and their cartographic elements. They can vary at spatial scales. They have very mixed resolution. So you can see, some of these maps could be a tiny building in Chicago or span the entire third of the United States. So you're really dealing with various heterogeneous cases. Project can also be multi-sited. So this kind of leads to quote-unquote visual forgetting when there's a project over there and it kind of forgets that actually part of the project's over there. And then there's this spectrum that happens with maps that are either highly cartographic, so there's all these human annotations on top of it, these legends, these scales, and then there's those that are just satellite-like, right, just photos of the Earth aerial, have no annotations to them. So how do we deal with them, and what does it kind of look like? So for those specific cases, to digitize these maps, so for example, the cartographic ones, there's a lot. So many components and so many AI tasks with them. You can get the bounding box, you can get the legend unit, you get scales, like I mentioned, figure references, polygons you can get extracted. You can classify them into different types and themes. There's a lot, and you can really look at the human annotation component to it. But then you have the more so, satellite-esque that are more just like images. These aren't really cartographic maps. And this is more defined by colors and textures and features and edge and contours. So you're dealing almost with a different visual semantic language for these models to understand. And so how do we do it? How do we use these kind of visual language models to actually get something out of them and put them on the Earth? So goal one, can we get them on the Earth? So first we parse it, like I mentioned. We use Docking, I really recommend, to be able to grab the images out of the documents and then classify them into map and non-map. So we have this map and metadata. Then we use several VLMs to do the cartographic unit detection, so identify all those items, classify these maps further, maybe into themes, and then be able to get a rough bounding box. We only go for rough because if you're trying to go for exact, it's not going to work at all. You're going to find that it's not going to work. But what can we do with this is that we can then go towards a vision-only model. So we say, okay, can you tell me generally where you think this is? And then feed that into a georegistry. Why? Because georegistries like Google Maps or OpenStreetMaps already have the Earth, geolocation. It has the image on the Earth. So let's grab that roughly, and then do kind of like a pixel-pixel match, essentially, between what is the map you want on the Earth versus the map already on the Earth, and see if you can get them to feature match, to compare. And that's where the vision-only model comes in. So we match feature descriptors, and then yay, we have a GeoTIFF in the end that's on the Earth. Sounds simple, but I will forewarn, not a great performance because there's a lot of gaps in these models. But there's some things we can improve on with, so project context improves this kind of location georeferencing process. So a lot of these projects have a lot of maps associated with them, and what you can do is just grab all the project context and improve that so you can get a better first bounding box. So you get a better bounding box versus if you just use a single map and no text. And then you can also, on the vision-only model, let's say like this map successfully georeferenced in a project. So okay, this was good to go. But then, well, this map was in the same project. Why did this fail, right? And these are quite old maps. You can see the issues, and you may never know why this failed, right? Was it because that lake has disappeared and since the last 10 years, right? Like, why is it? Well, what you can do is instead of taking the reference map to compare it between, you can actually just compare the success versus the failure, and then you can recover it. So you're able to scrape it and get more maps out of that. So that's the nice thing. Next phase. So the next thing is what you want to do is be able to extract layers using VLMs. And this is, I would describe this process as way more stochastic than the last one. So this one, you go in and you extract the legend units. And specifically, this is more like a color segmentation problem. You say, okay, what kind of colors are generally here? What kind of colors are here? Is there a match? You have a VLM in the process. And then we actually use the VLM as a judge to be able to iterate against itself because it's fairly stochastic. You have to go through several rounds until you get to a common color segmented out. Otherwise, the variances are what can be quite high between what's in the map content versus what's in the map legend. And then finally, the last phase is map classification. And this one gets quite interesting in a different way, in more a, there's so many map themes. And because you're not just considering what's in the world, right? You're not just like, oh, there's different land, agricultural lands, or there's different land zones. You're really getting into also like alternatives, things that are policy, regulatory, permitting specific. These concepts are more geared towards why was this map even made in the first place? So like, what's the purpose of this map? And one thing I'm really interested in that I would argue is that this is not really like a map classification problem, because permitting and siting are not just purely visual classification problems. They're not just optical illustrations. Really, what we should be thinking about this as is that, what if you were to embed Earth and permitting concepts into a shared latent space? And there's like a lot of literature on concept bottlenecks, which are very interesting. So just toss that word out there to explore more, but I think that would get us closer to be able to better geolocate projects rather than just purely thinking of it as a classification problem. This is only now to tell you, okay, so we do all these steps, and then what do we do about it? Well, we try to get it into your hands, we try to publish it, and so this is just to say we have a multi-cloud environment that goes in and does this all at scale for all those millions of maps and all those millions of documents, so it becomes into a data set that's on Hugging Face for you all. And we've had several versions and releases of this, so our 2.0 is actually released. You can use it for whatever research that you have. It includes these kind of structured schema elements, so you have your lead agencies, you have your project titles, project sectors and types, and your documents, and a rough location like you saw at the beginning. But the goal is pretty soon to go and then now release all the maps and images, as many of them as geotiffs as possible, as well as having the projects geolocated, so you have your project coverage. And this makes us ready for a world of agents, embeddings, and foundation models. So just to kind of reiterate, this is what we really aim to do. We're not just trying to stop at the data layer, we're trying to pump it into our applications as much as possible, because that's where our users are. We have over 600 federal users that are using our tools, and we're helping them through these drafting, writing, commenting period, all these processes that they have to go through. And also, as a quick plugin, but I won't go deep into it, MCPs, so, models, everyone's doing them, we're trying to pump as much more data as we can. So everything you saw before is historic data, now we want future data. So we're trying to federate as many authoritative data sources as possible to do map making on current data against historic data. So there's tons of MCP tools that we've been building. Think of them as functions that you put into a library that an agent can quickly orchestrate and call upon. And just to re-emphasize the kind of layering we want to be enabling in the near future. So just to recap, GeoAI is reshaping the pace and precision of permitting. We're going to see some huge advancements in this, and that's really where our position is in it. We're trying to hit as many permitting processes and siting processes as possible through it. It's very exciting, so I hope you'll join us and keep watching us. And I have a great team behind it, tons of people that I get to work with, which is fantastic. That we just presented, by the way. So yeah, thank you so much, and I'm happy to take any questions or any concerns. Okay.
We're too busy.
Yes, you are. Yes, check out the data. This is our project. You can read more. There's a lot of publications on there too, and a lot of other applications that exist in different ways. So this is like one part of the team of the project. Yes.
Yeah, something, sorry, I missed the first roommate, so if you mentioned it, then.
Oh yeah, I can always go back to.
No, it's fine. One of the goals of this project is to create like a very comprehensive label data of maps. I know that you use lots of VLMs and vision-only models to do the labeling. I guess in terms of like validating the labels themselves, I was wondering, can you say a little bit about it?
Yeah. So we work with a whole suite of subject matter experts for this entire data set. So for every metadata field we've ever parsed, it's been validated by experts. So yeah, I didn't put any numbers, but I'm happy to give you them for the performance-wise of things, because one of the biggest gaps when it comes to, so there's different tasks. So let's is there a particular task you want to drill in on?
Not particularly.
Not particular? Well, so for the geospatial, so the thing that really interests me on the geospatial tasks, especially the geolocating part, is actually how poor it performs in the literature and in our project. It's quite maybe at best you're getting 60% accuracy when it comes to being able to take something that you don't know where it's located. Not even just a map, think of a photo, right? You take a photo outside here, how does an AI know where you're at from that alone? It's not highly performant because these models are not great at geospatial reasoning. And so for us, it's a matter of having our SMEs validate things, and also we use a lot of Studio, we have a lot of validation sets, and that's really what we try to do. But the thing that we're running up against is that these models, even though they're state of the art and very big and performant, they're actually not good at this. So there's a lot of need to improve here.
Thanks.
Yeah. Okay. Thank you so much. Okay.